Welcome. Today I will be presenting our research on BAGEL, an approach to automatically detect navigation-based web accessibility barriers for keyboard users. Many people with disabilities rely on the keyboard interface to access the web. However, many web pages today are not designed or implemented in a way that is accessible to keyboard users. In this paper, we show 3 keyboard navigation violations (KNFs) defined by the WCAG that can prevent keyboard users from intuitively navigating the web app's UI. Here is an example of unintuitive navigation order from Disney's login page. When a keyboard user navigates the page and reaches the Create Account link, the keyboard cursor then jumps around the web page. For non-visual such as screen reader users, it can be disorienting when they encounter information in an order that is inconsistent with the content's meaning. Here is an example of unintuitive change of context from Mozilla's privacy page. As the user navigates to the language selection drop-down menu, if the user begins to browse the selections using the down arrow, the page automatically navigates to the Spanish version. For mouse users, they can go through all possible languages and click on their desired selection. However, for keyboard users, having the drop-down scripting activate the following language selection can be disorienting because they were not advised, nor confirm the action to leave the current web page. Here is an example of unapparent keyboard focus in the Guardian's login page. As a keyboard user navigates through the page, notice that it is difficult to tell where the keyboard cursor is. The Google, Facebook, or Apple buttons have focus that are displayed in a very faint gray highlight. These keyboard focus indicators can be problematic for keyboard users with low vision. In our paper, we present an approach to automatically detect these keyboard navigation failures (KNFs). The approach takes a web page as the input. It first models the keyboard navigation allowed by the web page. The model is represented as a graph where the nodes are elements in the web page and edges represent how the keyboard focus moves between elements based on keyboard interaction. In addition to modeling the focus navigation between the nodes, we monitor if the keyboard interaction causes the user to navigate away from the current page. We create a specially designated node called Exit to represent such action. Our approach further models 1. Semantic clustering, and 2. Visual representations of the elements. The approach uses a segmentation technique to group visually related elements in the web page together. The goal of this step is to model the way the web page's content information is structured and presented, which is often used to depict how users intend to interact and navigate the web page. Each node contains the visual representations of an element. This is done by capturing screenshots of the element both before and after it is set to focus to represent the exact way the focus would change and appear to a keyboard user during navigation. Once the models are constructed, the approach analyzes them to detect KNFs. For unintuitive navigation order (KNFs), we analyze the keyboard navigation model and semantic clustering model that was constructed. Our analysis is based on the insight that the elements within a cluster should have a similar semantic relationship and, therefore, should have an adjacent navigation sequence among other elements in the same cluster. Under such assumption, each cluster should have only one starting or entry point. This means a linear navigation flow should enter and exit each cluster exactly once. For the Disney login example, we see that the email text box and its More Info button are semantically grouped together, but they are not adjacent to each other in the navigation. The same applies to the password text box and the Forgot Password link. Our detection looks for any cluster with multiple entry points in either direction. Here, we see that clusters F2 and F3 have 2 incoming tab edges and 2 incoming shift tab edges. This represents that the keyboard navigation jumps around the UI and violates the linearity of navigation. To detect unintuitive change of context KNFs, the approach examines all the edges that lead to the exit node. Each of these edges represents a keyboard action that causes the page to navigate to a different page, in other words, a change of context. Here, we are only interested in those edges that represent actions not used for activation. Therefore, our approach identifies only those edges whose actions are Tab, Shift-Tab, or arrow keys. For the Mozilla example, many elements navigate to a different page, as shown in the blue edges leading to the exit node. The majority are links that navigate away via Enter. In this example, the KNF occurred by the edge that made the page navigate away via up and down arrows from the language drop-down node. This edge signifies that a change of context has occurred during the language selection process that is not intended for activation. To detect unapparent keyboard focus KNFs, we examine the visual representation model represented by screenshots of every element both before and after they are set to focus. The analysis identifies the visual differences between the before and after screenshots by checking if the contrast area is above the 2 minimum area thresholds defined by WCAG for sufficient visible focus. For the Google button example, the contrast area does not pass either threshold. The same applies to the yellow focus ring that outlines the email text box. In cases where the contrast area passes either threshold, then the approach performs additional analyses to determine if the color of the focus indicator and the color of the area around it passes a minimum contrast ratio of 3:1 as required by WCAG. This terms and conditions link example passes sufficient visible focus. After the detection, the output of our approach is a list of KNFs for the web page. To evaluate the effectiveness of our approach, we came up with 2 research questions, where RQ1 measures the accuracy of our KNF detection, and RQ2 measures the time. We implemented our approach as a Java prototype tool called BAGEL. We evaluated BAGEL's ability to detect KNFs in 20 real-world subject web pages and compared its results against 5 popular state-of-the-art web accessibility scanners. Here are the results for RQ1. BAGEL has high F1 scores for detecting the 3 types of KNFs. It is the only tool that can detect all 3 types of KNFs because it dynamically interacts with the web pages to model the runtime behaviors of keyboard focus. Most tools only scan the HTML properties of web pages. The results for RQ2 shows that BAGEL's runtime is longer compared to the other 5 accessibility scanners. By breaking down BAGEL's runtime, we see that most of the time was spent on building the models with only 2% of the time on the detection. This longer time is expected because BAGEL interacts with the subjects while taking screenshots to capture what a sighted user sees during their interaction. The higher time cost is a trade-off for its higher accuracy. We conducted an empirical study to qualitatively show the impact of our detected KNFs from the 2 complementary perspectives of developers and users. Developers were appreciative and personally expressed the importance of our findings. Many stated that they were addressing the issues or that our report could help improve the accessibility of their websites. The positive responses show that the issues we target represent real-world problems. On the other hand, we included a small user study to gather feedback from keyboard users with disabilities. Overall, the users did not find the web pages easy to navigate due to the KNFs. These responses verified that what BAGEL identifies as KNFs aligns with issues faced by real-life users with disabilities that rely on keyboard navigation. In summary, we introduced a keyboard focus flow model that uses semantic clustering and visual representation to formalize and detect keyboard navigation issues in WCAG. The evaluation shows that our approach was effective compared to the state of the art.